Good to see you. Good to have you here as well. Okay, good. Here we go. Pretty much the stuff that I've wanted you to look at this week, and this was specifically on Wednesday, was I wanted you to go through the statistics or the data handling from grade 11. So I did tell you guys you didn't actually have to go and watch that video. If you did watch the video, it gives a nice summary of all the statistics that you learned last year. So, and even the grade 10 stuff, if you think about it, I even did like a little summary of the grade 10 stuff where you did the discrete data and how to do the 5-number summary and how to do your standard deviation and all of that stuff on discrete data. And then when you look at your grouped data, which are grouped in classes or intervals, how to go and draw your ogive there, how to then also get your 5-number summary from your ogive, and then also how to use the group data to get an estimate of the mean and get an estimate of the standard deviation. So that's pretty much the statistics that you had to know for grade 11. Now the grade 12 statistics, good news about this is it's not a lot of work. It's actually a very, very small section. So we're going to introduce it today, and I'm pretty much going to do all of the operations today. And then when you come to school on Monday, we'll do lots of practice. And we're also going to do just a couple of, those level 3, level 4 questions. Because even though the basic work is very basic and quite easy to do, they can bring in some more insight, which, like I said, is more like a level 3 or level 4 question. And that specifically has to do with outliers, and that's what we're going to discuss on Monday. We're going to keep going with the bivariate data, but we're going to talk about the effect that outliers have on bivariate data. So let's start with bivariate data and what it is. So bivariate data says when each item in a population has 2 measurements associated with it. So mostly what we've done up until now, is we will take all the people in the school, for instance, and we will measure their length only. So that's what we call univariate data, single variable data. So all the people in the school, we will only go and measure their length, and we will only record their length. Bivariate data is something different. So every single person in the school lines up again. But instead of just measuring their length, we also measure their weight. And that length weight is then what we call by2 variable data. Now, those 2 measurements need to stick together because obviously we don't want to go and collect all of the weights and chuck it somewhere and just arrange it from smallest to biggest, and then collect all of the heights and just arrange, or lengths, and just arrange that from smallest to biggest. We want to keep them together. And it's a very good reason why we keep those 2 data items together, the bivariate data. Right, so that's pretty much what bivariate data is, collecting 2 measurements for each item. So maybe for each person in a population, we collect 2 measurements. So in the example I've got here is we'll say each learner in the school that has a physical sciences mark also has a mathematics mark, because obviously you can't take physical sciences unless you take mathematics. So what we would do then is we would then go and say, and randomly, we'd say a learner has got, say, 60% for mathematics and say 70% for physical sciences. So I'd put a dot there. So the dot will be an XY coordinate dot. X will in this case represent the mathematics mark, and Y will represent their corresponding physical sciences mark. So I can have somebody, for instance, who's got 75 for mathematics and maybe about 80% for physical sciences. So I'll put a dot there, which represents that person's mathematics mark, physical sciences mark. Or I'll have a person who'll have 50% for mathematics and might then have about 48% for physical sciences, and I'll put a dot there. So eventually, for every single person, there will be a dot. And you can then go, and from that dot, you can read off for that particular person. This went a little bit too far. That person's got, that went way too far. So let me just erase these dots. That's better. So this person might then have about 90% for mathematics and about 91% for physical sciences. So each one of these dots, X coordinate represents the mark for mathematics and the mark for physical sciences. But each dot is a person in the population. Okay. Now this diagram you might have encountered before. It's called a scatter plot. a scatter plot or a scatter diagram. So it's just a scattering of all of the marks that we have collected, but specifically bivariate data, two measurements for every single item. Okay. Now, the reason we do this is because scatter plots can show a correlation between the two variables. Now, the word correlation, we're going to use that more and more and more in this bivariate data. Another word for correlation is association. So the scatter plot can show an association or correlation between the two variables. Meaning, if you look at these marks, you can already have, like, in general, like a feeling of the fact that the bigger the maths mark, the bigger the physical sciences mark. That's what it kind of looks like. It seems to be an association, there seems to be a correlation, and that's the stuff we're going to be talking about in this bivariate data. Now, first thing we need to talk about this correlation, and we are going to spend quite a bit of time talking about the correlation between the variables. The correlation can either be linear or non-linear. Now, linear correlation means that if I look at the dots in the scatter plot, they seem to look like a straight line. They seem to look like a straight line. If I were to draw a nice big thick straight line, you can actually see how all of those dots would fit on that nice big thick straight line. So linear means you get this idea of the dots following a straight line. But the correlation could actually also be non-linear. The correlation could actually look something like this, which hopefully you guys should recognize. Again, if I had a nice thick marker and I had to go and draw across those dots, you guys would maybe recognize this would be a parabola. So this is quadratic. So correlation can either be linear or non-linear. We can actually have parabolas, we can have hyperbolas here, we can have cubic graphs even, we can have any graph over here, which is then a non-linear correlation. Now, the good news is we do not look at non-linear correlations at all. You have to be aware of the fact that there are such a thing as non-linear correlations, but we don't deal with them in core mathematics. All of the correlations we're going to be dealing with are going to be linear correlations. But just to tell you that you do have non-linear correlations, that is definitely possible. But we're going to be focusing only on the linear correlations. Right, so now the next thing that we can say about a correlation, if we're only going to look specifically here at the linear correlations, because remember, we're not going to look at the non-linear correlations, only the linear ones. Correlation can be positive or a correlation can be negative. And that just pretty much refers to the slope or the gradient of the line. Meaning, if I have the dots again that kind of look to be forming a straight line, then this seems to be a straight line with a positive gradient. So this is positive because as x increases, y increases. So if you look at that very first example that I had over here, as the mathematics mark gets more, the physical sciences mark gets more. That is a positive correlation between the two variables. So this is positive. Whereas you could also have a correlation that looks like this. So if you look at the scatter plot, you'll see as the one value gets more, as the one variable gets more, the other variable gets less. And that does look, if you had to draw a line there, a nice thick line, it does look like a line with a negative slope or a negative gradient. So this is what we call a negative correlation. There we go. Okay. Then correlations can also have a certain strength associated with it. So a correlation can be strong, it can be weak, or there could potentially be absolutely no correlation, depending on how closely these dots are together. So a strong correlation means the dots are actually fairly close to being on the same straight line. You see, so if you were to go and you were to draw a straight line over here, the dots seem to be very close to the straight line. So this is what we would call a very strong correlation, by the way. This will be a very strong correlation. These dots, for instance, up here, we actually will refer to as strong or significant correlation. But we'll talk about how to judge the strength of correlation a little bit later on. But this is a very strong correlation. Then a correlation can also be weak. So a weak correlation, there's still a trend to the data. You'll see it still looks to be a line. It still looks to be going kind of up, but you'll see the dots are much more further spread apart. So this is what we will call a weak correlation. And then no correlation, I always say to people, looks like a swarm of bees. So if you put the dots everywhere, like this, like a big swarm of bees, there's no way you can tell me this seems to be forming a straight line. It doesn't. There doesn't seem to be, is it positive? Is it negative? Is it a straight line? This is pretty much no correlation. So again, just to recap, correlation can be linear or it can be non-linear. But the good news is we are not going to be doing these non-linear correlations at all. You need to be aware that they exist, but we are not going to be doing these. So these ones you can ignore. So whenever you describe a correlation, you will always describe a correlation as linear because we only do the linear correlations. Then the second thing is it can either be a positive correlation, meaning that the straight line has got a positive slope or a positive gradient, or a negative correlation, meaning it's got a negative slope or a negative gradient. And then correlations can be strong, weak, or there could potentially be no correlation. And by the way, if you use the description saying there's no correlation, you're not going to describe it as linear, positive, or negative. No correlation means there's no correlation, so there's no point in describing it as linear, positive, or negative. Okay, so it's a bit difficult to discuss the correlation unless you have a measurement, a mathematical measurement of the correlation. And that mathematical measurement of the correlation is what we refer to as the correlation coefficient. So the correlation coefficient measures the strength of a linear correlation between two variables. So if I've got those two variables, all of those coordinates, remember, because each one of these points has got its own coordinate. It's got an x coordinate, y coordinate. That point's got an x coordinate, y coordinate. So each point has got that x, y. So if we go and we have all of those variables, those x, y variables, we can measure the strength of the linear correlation. And like I said, we're only going to look at linear correlations. We're not going to look at non-linear correlations. And we determine that by looking at R. R refers to the correlation coefficient. So that R is the symbol for the correlation coefficient. And a correlation coefficient can lie between -1 included and +1 included. So my correlation coefficient, the biggest it can be is 1, and the smallest that it can be is -1. And then it can take on any value in between. And looking at that correlation coefficient, we can then comment on the strength based on that correlation coefficient, whether it's positive, negative, based on the correlation coefficient, and then we're always going to make the comment that it's linear. That's why I put an asterisk there, because we're not going to look at correlation coefficients for non-linear correlations. All of our correlations are going to be linear. That's very, very important to remember. Okay. So this is in your textbook on page 332. And this is pretty much your description of all the correlations. So if a correlation is equal to +1, that is what we refer to as a perfect correlation. So a perfect correlation, if I imagine that as a scatter plot, literally means the points look like they lie on the same straight line. So it pretty much would look like this. If I had to draw a correlation of 1, it would be like this. That is about a correlation of +1, because you can go and you can draw a line and all of the points pretty much fall exactly on the line. It's a perfect correlation. Okay. Then we can have a correlation that lies between 0,9 and 1. This is what we call a very strong positive. And the nice thing about the positive-negative correlation is obviously the sign of the correlation coefficient will tell you whether it's positive or negative. You'll see over here, we have positive correlations, And then over here, we start with negative correlations over there. So every single time we hit a negative R value, you'll see we use the word negative, 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 negative. So that's a nice thing at least, is if R is positive, we call it a positive correlation. If R is negative, we call it a negative correlation. It's pretty much only that the strength of the correlation that you guys have to get used to over here. So correlation can be perfect. It can be very strong, which normally means it lies between 0,9 and 1. It can be significant or strong. You can either use the word significant. The textbook uses the word significant or strong, and that is normally between 0,7 and 0,9. But please don't say a correlation is very strong if it's less than 0,9. It's only very strong if it's more than 0,9. And I would suggest rather use the wording significant here. Don't use strong here, use significant. Okay. If the correlation is between 0,3 and 0,7, the correlation is considered to be weak. If the correlation is less than 0,3, then we pretty much say there's no linear correlation. So any value that lies between minus 0,3 and positive 0,3, we say there's no linear correlation, and therefore we don't have to comment on the positive or negative. We can just say no linear correlation. Then over here, this is just, if you think about it, the reverse of that. This is a weak negative linear correlation. This is a significant negative linear correlation. This is a very strong negative linear correlation. And this is a perfect negative linear correlation. So every single time you will comment on all three of those things. And the lovely thing about commenting on all three of those things, this thing is pretty much always true unless there's no correlation. So it's always linear. And this, you will just look at the sign of the R value to decide if it's positive or negative. And this one is the only tricky one where you have to obviously go and look at the numbers to decide if it's perfect, very strong, significant, or weak. But it's all there on page 332. And then if you are using other books, you'll see other books actually have other descriptions. So a lot of the books will talk about strong, but they won't mention the word very strong. A lot of the books use the word significant, but they use different values for significant. And that's why there's quite a bit of leeway on the strength description. Meaning if you use significant, but they wanted strong, they'll give you the mark. Just be careful, because if they wanted weak and you use the word strong, they're not going to give that to you. So yes, there's leeway on the description, but there's not that much leeway. So be careful there. Okay, so how do I calculate the correlation coefficient? Good news about calculating the correlation coefficient, it's all calculator-based work. All of it based on the calculator. Okay, so I've written the calculator steps down over here. First thing you have to do is you obviously have to go to your stat mode, just like you did with the grade 11 statistics. So we'll go and we'll say mode, and we'll select mode 3, which is stat mode over here. By the way, that 3 is for the silver calculator, because I think most of you do have the silver calculator. Obviously, if you have the black, the pink, or the blue calculator, you just have to press your button for the stat mode. I don't think it's 3. I want to say it's 2 on the black calculator, if I'm not mistaken, but the rest is all the same. It's just this one that is different on the black, the blue, or the pink calculator. Okay, now comes the only tricky bit. This is the only tricky bit. Up until now, and especially if you did that worksheet on the grade 11 stats, you always used button number 1, because button number 1 stood for one variable. Because all of the data you've dealt with so far in statistics were one variable or univariate data. It was all just one set of items for the population. But now we are going to be pressing button number 2. And I want you to look at that button number 2. It doesn't say bivariate data. But what it does say is it says a plus bx, like I've written over there, a plus bx. Now that a plus bx, we'll talk about it just now, is the equation of a straight line. Y is equal to a plus bx. It's the same as saying y is equal to mx plus c. They just don't use m and c as the coefficients. They use b as the coefficient of x, which by the way is the slope of the line. And they use a, which is like the constant, the c value, which is going to be the y-intercept of the line. So you have to recognize this is the one we're using, because because all of the regressions, and I'll talk about the word regression just now, all of the regressions we're going to be doing are going to be linear, going to be straight line. So we only use that button number 2. By the way, if you look at the other buttons, this is where you can see that's quadratic. So that's if you want to do a non-linear quadratic regression. There even is lin, which you don't know for core maths, that's a logarithmic regression. So none of the rest of these are anything we're going to be doing. You can completely ignore button 3, 4, 5, 6, 7, 8. We're only going to be using that button 2 for the straight line, the linear regression. So we press 2. Then what pops up, what has never popped up before, is xy. So that means we need not only the x coordinate, we need the corresponding y coordinate. So I've gotten an example here from a past paper. Here we go. And in this example, it says, the shoulder strength and the number of push-ups done per day by a random sample of 12 18-year-old boys were recorded as shown in the table below. So they're saying they, for each boy, collected 2 sets of variables. So an x variable and a y variable. So for each boy, they said, let's look at the number of push-ups you can do, and let's also check the strength of your shoulder. Let me just see if I can fix the focus here. It's a little bit blurry, sorry. That's a bit better. Okay, so each one of these represents one boy. It's that single boy's push-ups and strength shoulder. It's another boy's push-ups and strength shoulders. It's another boy. So, and these are together for one boy. You can't mix and match. So you can't go and say, oh, let me arrange this from smallest to biggest, arrange this from smallest to biggest. They've got to stick together. That XY is based on one single person. So that XY value has got to stick together to represent that one single person. So when you type these XY values in, be very careful. They'll tell you which one is X. By the way, if they forget to tell you which one is X, it's always going to be the first set of data is always going to be X, and the second set of data is always going to be Y. Now, you can type it in separately. You can type in all the X's and all the Y's, but you have to make sure they stick together. Please, people, I cannot stress enough. If you mix it up, if you put a different Y value with a specific X value, nothing works. Everything's wrong from then on. So I'm just going to type these in, 27, 165, and then the nice thing, if you type in the X values quite quickly, when you type in the Y values, you can actually check the X values because you have to check that they correspond anyway, that they're the same one. So you can check 27 check, so that's going to be 0.2. The next one, 165 check, so that's going to be 0.98. And please make sure it's accurate. The biggest reason I say it's got to be accurate is because all of this work is done with your calculator. If you mess up one single value, like you type it in incorrectly, we pretty much can't give you any continued accuracy marks because we don't know which value you messed up. You see what I'm saying? So if you typed in 157 there instead of 156, that won't make that much of a difference. Let's say you swapped around. Let's say you typed in 165 instead of 156. Then everything from then on for you is going to be wrong. And I'm going to be forced to mark it wrong because there's no way I know which value you messed up. So there's no way I can give you continued accuracy because I don't know. So please, please, people, I cannot stress enough how accurate this calculator work has got to be. It's got to be perfect, please. So take your time in entering this.
Ma'am?
Yes.
From what paper is this? What year is it?
This is the 2018 supplementary paper.
Okay, thank you, ma'am.
But I will, like I always do, I'll make sure that I put the copies onto the Google Classroom for you guys.
Thank you, ma'am.
Sure. And then you've got the 20, 0.15. Sorry, this takes a little while. And then the 0.78. And then the 56, 0.4. And the 158, 0.95. There we go. So we've got all of the data items. Now going back to how to do it on your calculator, the next little thing you have to remember is enter the bivariate data. And again, I said they keep the measurements together, meaning do not go and type in a Y value, a different Y value to a specific X value. They've got to stick together. Now, The rest is you press the AC button, and I've said this to you guys before, only once to clear the screen. If you press it twice or more, you might actually clear the data, so be very careful there. You press the AC button once. Then you press the shift button, and you press the 1 button because that stat lies above the 1 button. We press that. Now you have this option coming up, 5, which is regressions. So just to explain to you why we press button 5, which is regression, is we are going to take these points and we're going to regress the points back to a straight line. And that's why it's called a line regression, and that's why we use button 5 for that line regression. And then you've got lots of values there. We'll talk about the other values just now. The one we're focusing at the moment is R, number 3, which I did explain to you guys is your correlation coefficient. So number 3, I press 3 and I press equal. So now we can go and we can say the correlation coefficient here for this particular example that we're busy doing. So let's write that down, because that was the first question. Calculate the correlation coefficient, round off to 3 decimal places. And please, people, you guys can be very, very, very slapdash about your rounding off sometimes. You need to make sure you read it this carefully, because I'm fully aware of the fact that your IB papers normally on the very first page says round off to 1 decimal place unless the question states otherwise. And then some of you guys just stick with that. You round everything off to 1 decimal place. Even though we have told you multiple times, like in finance, you always round off to 2 decimal places. And a lot of the time in your measurement stuff, like in your trig measurement, they ask you to round off to the closest degree or round off to the closest square units. So please, people, read your question carefully and stick to the instructions they give you there, which was round up to 3 decimal places. Now, once you've gone and you've calculated that correlation coefficient, they generally ask you to describe the relationship based on the correlation coefficient. So this is something you normally have to be ready for immediately, that discussion of 3 things. Number 1, strength. Number 2, positive or negative. And number 3, linear. Even if you say that it's always linear, why should I say the word linear? You still mention the word linear. Okay. So can anybody tell me 0,973? What strength will I say is this? Come on. This should be very obvious. This is an easy example. What can you say about a strength of 0,973?
It's very strong.
It's very strong, absolutely. The closer it is to 1, if it's positive, the stronger it is. And then obviously the closer it is to -1, if it's negative, the stronger it is. That's pretty much the rule of thumb. The closer you get to 1, the stronger positive it is. And the closer you get to -1, the stronger negative it is. So I can say this is very strong. And because R is positive, it's very strong, positive, linear. And these are some of the easiest marks you can get in your paper. Okay, right, so next we have to talk about, which is the second set of calculations we're going to be required to do on this bivariate data, is what we refer to as a least squares regression line. Now, some of the books and some of the notes you might get refer to this one as a line of best fit. So let me just put it here and explain to you that it's not actually the same thing. A line of best fit and a least squares regression line is not the same thing, but some of the maths teachers who wrote books, they're not very good at stats. So they use these 2 terms interchangeably, like as though it's the same thing. But I'll explain to you just now, there is a difference between the 2. So it's line of best fit. A line of best fit means you are going to take a ruler. I don't seem to have a ruler with me at the moment, but you will take a ruler and you will look at the points, okay, of the bivariate data, and you will try and fit a straight line onto those points, the line of best fit. And I will then generally go and say, I need to go through as many points as possible, but I also need to make sure that I have the same number of points above the line as below the line. So that means in general, the line of best fit is going to be round about there. That's round about where the line of best fit is going to be. But most of you guys, especially those of you guys who are very OCD and who are very perfectionistic, you'll look at that and go, I need a rule. I need a rule as to where to put it. And that, unfortunately, I can't give you. I can't actually give you a rule for a line of best fit, because a line of best fit is pretty much, it's a sort of almost kind of guessing game. That's what a line of best fit is. Okay. Whereas the least squares regression line is much more accurate. It's much more accurate. It's mathematical. It actually has a mathematical formula. We're not going to look at the formula because we're going to let the calculator do the job for us again. But pretty much what the least squares regression line does is when it draws a line, it looks at the distance between each point and the line, and then it draws a little square. Looks at the distance and it draws a little square. Looks at the distance and then it draws a little square. Looks at the distance and then it draws a little square. And pretty much the line then gets moved up or down until these squares, they add the area of all of these squares. So the moment the area of all of these squares added together is at a minimum, then they go, that's the line we go with. Which actually, if you think about it, makes a lot of sense, because what it does is it limits the distance the points have to the line. So it works out the distance the points have to the line. And by the way, the reason it's the squares is because some of the distances are positive, you have to go up, but some of the distances are negative, you have to go down. But if you square it, then all of it becomes positive. So then you don't have distances being added and subtracted, you just have square distances being added. So pretty much all that happens is it adds all of those square distances, and whenever we have the smallest distance between the points in the line, that's what they call the least squares regression line. That's just to give you an idea of how it gets done. However, the calculator is going to do all of it for us. So you don't actually need to understand this. You just need to be able to do the procedure of this least squares regression line. But heads up, people, if they do use the word line of best fit and they say use your calculator to calculate the line of best fit, they actually mean the least squares regression line. So apologies, in IB in general, they always call it the least squares regression line, but especially I've noticed in some of the government papers, they often call it the line of best fit, even though it's not the line of best fit, it's the least squares regression line. Okay, so that being said, the first steps for the least squares regression line is exactly the same as we followed for the correlation coefficient. So I've already got all of that data stored in here. So if you had to go and do a brand new example, you'd again press mode, stat, select number 2 for your linear regression, and then you'd enter your bivariate data. I'm not going to do all of that again because my bivariate data is already entered into the calculator. I'm just going to go to this. So I press the AC button to clear the screen. I press Shift, to show you here, I press Shift, Stat, and then I go to number 5 where all of my line regressions happen. There. So number 5 is where all of my line regressions happen. And then you'll notice that before we had that R, the correlation coefficient, we had A and we had B. And if you ever forget what A and B is, please remember that very first button you pressed told you A is the y-intercept of the least squares regression line. B is the gradient of the least squares regression line. And a lot of the time they even write it like that. They never write the least squares regression line y is equal to mx plus c. They always write it y is equal to a plus bx. That's the way you have to stick to. That's the way we had to do it in stats. So remember y is equal to a plus bx. So if I go back to that example that we're busy doing, it says over here, determine the equation of the regression line. So they call it a regression line, which is just another name for the least squares regression line. And write your answer in the form y is equal to a plus b. So like I explained, they even want you to write it in that format. And look carefully at this, round off to 4 decimal places. Please, people, do not lose marks because you're not reading the instructions for rounding. Please, please, please. So we're going to go and first press 1 and then press equal. And that is going to be my A value for that least squares regression line. So I can write y is equal to 0,0981. So that's the A value. And then we're going to go and we're going to type AC again. We're going to go shift, stat, regression, so number 5, and then B for the B value of that line. And this one, unfortunately, as you can see, is written in scientific notation. So hopefully you guys will know with scientific notation, it's going to be plus 0,0057, and you can just check because this is supposed to be 10 to the power of -3. So if I move this comma 1, 2, 3 spaces, then it's at the right space. So that's why they wanted it rounded off to 4 decimal places, just because this B value is so tiny. Okay, and please don't write it in scientific notation. Please, you need to write it rounded off to 4 decimal places. And if you wrote it in scientific notation, rounded off to 4 decimal places, they would penalize you for that. You can still use it, but they will penalize you because that's not 4 decimal places. 4 decimal places here is that 0,0057. And then we put the X down. So that then is my least squares regression line. Now, just a quick comment. I just want to show you one thing over here. If I press the AC button again and I go shift, stat, and I press regression, the other two that you've got here, you'll see they've got X hat over there, X with a hat, literally, and you've got Y hat over there. It's Y with a hat. This X hat, Y hat. X hat is the mean of all the X values that you typed in the original set of data. Y hat is the mean of all the Y values that you typed in. But the good news is you don't even have to use this because, just to show you, if I press AC again, and I press shift, stat, here under variance number 4, which we've used before, it will give you, look at all of this, X bar, which is the mean of all the X values, Y bar, which is the mean of all the Y values, and it even gives you sigma X and sigma Y, which is the standard deviation of all the X values and the standard deviation of all the Y values. So if they do give you bivariate data and they ask for the mean of the X values, they can't ask for the mean of the bivariate data. There's no such thing. But if they do ask for the mean of the X values, you can just use a calculator. You don't have to retype all the data in. You can just use this bivariate data because you can get the mean of the X values, the mean of the Y values, the standard deviation of the X values, the standard deviation of the Y values. But it's impossible to get the standard deviation of all the values. That doesn't work. That can't happen. Okay. Right, next. Now, let's talk about what we use this least squares regression line for. Least squares regression lines are used to make predictions. So we're going to make predictions based on this mathematical or statistical model. So we've now established a statistical model that says there's a relationship between X and Y. There's an association. There's a correlation between X and Y. So logically speaking, I can substitute any X value that is not in the data. So for instance, if I look at this original data, there was no boy that could do 35 push-ups. As you can see, there was no 35 push-ups over there. So I can take 35, which is not in the data, and I can sub 35 into X, into my line, and then I can make a prediction based on this correlation of what Y is going to be, what the shoulder strength is going to be. That's the whole goal with a regression line, is that you develop a statistical model where you can actually predict the value of Y based on what X is going to be. So that's exactly the question they ask here. They say, use the regression line to predict the strength of an 18-year-old boy's shoulder if you know he does 120 push-ups per day. And they say use the regression line. So all you have to do is you have to say, we use that regression line, Y is equal to 0,0981 plus 0,0057, and we multiply by X, which is the 120 push-ups this boy can do. Now, obviously, I need to change my calculator back to computer mode. By the way, people, do not change your calculator back to computer mode unless you've done all of the calculations. Meaning, unless you've done R and you've written it down, you've done the A, you've done the B, you've written it down, do not change your calculator back to computer mode Otherwise, please remember all that data that I typed in right at the beginning is lost the moment you change to computer mode, which means if you accidentally forgot to write down the A and the B value, you're going to have to go and re-enter all of that data in order to get the A and the B value. So that's why I always say, just make sure you've written down R, you've written down A, you've written down B. Good, I can then change the calculator mode. So I'm going to change to computer mode. And I'm just going to type this in, 0.0981 plus 0.0057 times that 120 push-ups. And this model, this regression line, then predicts the strength is going to be 0.7821. That's the predicted shoulder strength of a boy who can do 120 push-ups. Now, generally what you then want to do is after you've done a prediction, you want to comment on how accurate this prediction is. So you want to say, I now predict that a boy who can do 120 push-ups has a shoulder strength of 0.7821. But then people are going to go and say, oh, that's great, but please explain to me, is this an accurate prediction? Yes or no? And this is very important. You need to please be aware of this. When we use these lines to make predictions, we talk about interpolation, that's the first word, and extrapolation, that's the second word. Now, interpolation means the value, the x value that we substituted into the line lies within the domain. And when you ask what's the domain, it's quite simple. If I look at x over here, the smallest x value that we had there was 20. The largest x value that we had in the original data was 165. So if I substitute an x value into the line between 20 and 165, we call it interpolation, because the value lies within the interval or within the domain of the x values. Okay. But if I substitute an x value into that regression line that lies outside, so in other words, smaller than 20, like 10, or a value that's greater than 165, like 200. So if I substitute values in that don't lie within that domain, we call that extrapolation. So interpolation, which this is, by the way, this is interpolation, because 120 does lie between 20 and 165. So this is what we call interpolation. But if I, for instance, went and I substituted 200 in there, then that would be extrapolation. Or if I substituted 5 in there, that would have been extrapolation, because those values do not lie within the domain of my original data set. It's always got to be the domain of the original data set. So why are we talking about interpolation and extrapolation? Interpolation, the accuracy depends on the correlation coefficient. So if the correlation coefficient, like with this one, shows that we have a very strong correlation, then that means this is accurate. So if we now say, is this accurate or not? We can say, yes, it's interpolation. And I know that they didn't ask it here, but I'm going to write this down anyway. It's interpolation. You always have to mention if it's interpolation or extrapolation. So it's interpolation. I always forget how to spell it. Interpolation. Interpolation with a strong correlation. So yes, it's accurate. And it's actually not just strong, it's a very strong correlation, so it's accurate. Therefore, it's accurate. This is an accurate prediction. Okay, well, as accurate as a prediction can be. Now, this question says, an 18-year-old boy does 280 push-ups per day. Can your regression line formula predict the strength of a shoulder? Explain your answer. Now, a lot of people, they just look at the correlation coefficient and they go like, yes, correlation is very strong, so it can totally predict the answer. People do not look at the correlation coefficient unless you've determined whether it's interpolation or extrapolation. Now, if you look at the fact that they want you to substitute 280 into x, and if you look at the original values which lie between 20 and 165, is this going to be interpolation or is this going to be extrapolation? There's somebody awake still out there. Hello? Are we still on here? Have I lost?
Extrapolation.
Thank you. It's extrapolation. And people, extrapolation is always inaccurate. Always. It doesn't matter how strong that correlation coefficient is. Extrapolation is always, always inaccurate. Let me explain to you why extrapolation is always inaccurate. Because you might have gotten a lovely scatter plot where the values looked like this, which was very clearly very, very strong. But these were all the values you had. This was your, as I explained to you, this was my domain right there. That was my domain. And we only collected these values. Now, it was quite possible that after this, it passed this value. Suddenly, the values did this. We don't know what it did after it passed that domain. So we might have a very strong positive correlation over here within the domain. But the moment you pass outside the domain, the data could have done something completely different. You cannot go and make any prediction about what the data did outside that domain. You can only go and talk about what the data did within the domain. And that is why when it says the 18-year-old boy does 280 push-ups per day, can your regression line formula predict the strength of the shoulder? No. And the reason is always going to be this will be extrapolation. And they want you to know these words, interpolation and extrapolation. You need to know this. If you do forget the word in the exam, like if you go like, oh damn, I can't remember that word, you will just then have to go and describe it. So you will say, no, it's not accurate because 280 does not lie within the domain of the given data set. So that's pretty much what you're saying. You're just giving the explanation of extrapolation rather than using the word extrapolation, but you do need to know either one of those two. Okay. Right. Let's do one more quickly since we have a little bit of time here. And I'm going to try and put it on the screen so you guys can actually grab your calculators and try it on your own. So if you do have your calculators, let's just go through the steps. You'll go mode, stat mode, number 3. You'll select A plus BX because this is bivariate and we want to do a regression analysis. So we're going to press 2 and then you can just enter that. That should be clear enough for you to enter. And like I said, enter the X values quickly, that's fine. But when you go back to put in the corresponding Y values, just check those X values, make sure it's accurate. Okay, so once you've typed in the values, you press AC once, you press Shift, you press Stat, and you press 5 for regression. And like I said, then it depends on which question they ask. And please, people, do not change the mode until you've written everything down. Okay, so the first question, determine the least squares regression line in the form y is equal to a plus bx. Give your values for a and b to 4 decimal places. So I'm going to need the value for a and for b over there. So I'm going to press 1 for a. And that means y is going to be equal to 51, 6478. Did anybody follow along? Did anybody get the same value there for A?
Yes, ma'am.
Excellent.
Yes, ma'am.
Then we press that AC button, we go Shift, Stat, and then we press 5, regression, and we press 2 for B, and we get plus 0.7776x. Please don't forget that X. Okay, now one comment that I forgot to make, your B value and your correlation coefficient will always have the same sign if you think about it. because your correlation coefficient, if it's negative, it indicates a negative correlation, which means a negative gradient, which means a negative slope. So that means if your B value is positive, your R value will be positive, and vice versa. If your R value is negative, your B value will be negative. They won't be the same though. Just be careful. Don't assume the B and the R value are going to be equal. They're not. They're just going to have the same signs because they mean different things. Okay, so we've got that. Then this was a mean question because suddenly they ask, use your answer to extrapolate the score that a learner would obtain. But if you just skip ahead to the bottom here, calculate the correlation coefficient. So if you had then gone and you'd press the AC button to do this question, you would have had to enter all of that data again to get to the correlation coefficient. And that's why I always just skip ahead to check that they don't ask for the correlation coefficient. So I can just quickly do that first. So I'll press the AC button, Shift 1 for stat, regression, and then R for correlation coefficient equal. So R over here, and they say, calculate the correlation coefficient of the data to the nearest whole number. Now, I hate this question. I hate it. I'm going to write it down to 4 decimal places, 0,8291. If you round it off to the nearest whole number, I'll just write it over there, then R is equal to 1. And then you'll understand just now when we get to the rest of this question why I hate it so much. Because there's a massive difference between a correlation of 0,8291 and a correlation of 1. Massive, massive difference. So they should actually not have asked this question at all. But anyway, right, so B over here says, use your answer to A to extrapolate the score that a learner would obtain if they practiced 100 examples. So we can just change this to calculator mode or computer mode, and I can then put that in there, 51.6478 plus 0.7776 times 100. And this is going to be, and there they say, give your answer to the nearest whole number. By the way, I always give it rounded off to whatever decimals, and then after that, I will then do this sign to show that I'm rounding off. Because I like having the original and then having the rounded off one so I can just compare this. This is a very good habit, by the way. So rounded off to the nearest whole number will be 129. But I will show this first before I do the rounding off. Now it says comment on the answer in B. Now when they ask you to comment on the answer in B, it pretty much refers, is it accurate or not? So they even went and they were very nice to you. They did this. They used the word extrapolate. So comment on the answer in B. This is extrapolation because as you can see, 100 doesn't lie anywhere close to these X values. I mean, the biggest X value we've got is 60. So 100 is quite far from the biggest X value. So because this is extrapolation, it's inaccurate. So inaccurate due to extrapolation. And then this question, calculate the correlation coefficient of the data to the nearest whole number and describe it. I would not describe this because this describes a perfect positive linear correlation, whereas this one describes a significant positive linear correlation. So that's why I thought this was really badly asked. This was the 2016 supplementary exam. Back then, they weren't very good at the stats. They've really cleaned up the stats quite nicely. So they don't do stuff like this anymore. So I will just refer to this and I will say it's a significant positive linear correlation. And that's pretty much it. And as you guys can see, we are going to look at more complicated questions on Monday when we talk about outliers and the effect outliers have on the bivariate data. And then I'll show you like the level 3, level 4 questions. But I think you guys can all agree that these ones are so lovely. They're absolutely glorious to do. Even the more complicated stuff that we're going to speak about on Monday, once you see the changes that can be brought in, you'll realize even that is not that complicated at all. So I always say this is like the one section that you can easily get 100% for. And I will also give you a photocopied worksheet on Monday where you guys are going to sit and you're going to work through it and you're going to practice these ones and do as many of these as possible within the changes that outliers bring in. And then pretty much Monday we're going to be finished with this work because this is all of it. As you can see, it took less than an hour to discuss all of it except for the effect that outliers have on it. So that's a nice little work to do. Okay. Any questions? Going? No, I'm not going to give you homework over the weekend. Like I explained to you guys, I'll give you a worksheet on these ones, the easy ones as well as the harder ones on Monday. So on Monday, you will practice these things. Please, over the weekend, no maths for you guys. I just wanted to go through this content so that when we get to Monday, you guys know what's going on and you can practice it. Okay.
Thank you, ma'am.
Thanks, ma'am.
My pleasure. I'm going to stop the recording now.